Okay, thank you. This presentation will be English. So hello everyone. My name is Suihan Zhang, and I'm currently a PhD student at KTH. In this presentation, I'm going to talk about the design of Grout curtain. This is part of the PhD project financed by SEC, and Fredrik Johansson is the main supervisor. Today's presentation will consist of 4 parts: background and new design concept for Grout curtains, design sample, and a future work. First, a short background about Grout curtains. Grout curtains are constructed under dams to reduce the hydraulic conductivity of the rock foundation, and then to reduce the water leakage through the rock mass, and also help to reduce uplift pressure. Previously, the Grout curtain design was mostly empirical technique. The design was based on rules of thumbs and experience. It has certain limitations, such as quality of the Grout curtain relies heavily on the experience of the designer, and lack of experience could lead, or understanding of the geological condition can lead to inadequate or conservative design. And internal erosion of the fracture in fitting materials is not directly taken into consideration from the previous empirical design. And the stop criteria used in the previous design method was called refusal or minimum flow for a period of time. And that can lead to very long grouting time, which is not so efficient. Also about grouting pressure, hydraulic jacking can occur if grouting pressure is not properly chosen. In recent decades, extensive research on grouting has been performed at KTH and Chalmers and some other places in Sweden, in the world as well. And so now it's possible for a more theory-based design method, and of course under the framework of observational method. So now I'm going to talk about this new design concept for Grout curtains. Firstly, about what I have been doing is that the existing grouting theories are mostly got from previous researchers, and what I'm doing is to collect them, learn, understand them, and rearrange them into a systematic design concept in the context of Grout curtains. Because previously the grouting theories was, some of them, they were focused on the terminal grouting as well. So the new design concept for Grout curtains is presented as a design flowchart, which is composed of preliminary design, as it shows in the first block here, and grouting execution, and with a monitoring and maintenance after the grout curtain has been constructed. In today's presentation, I will introduce more in detail in the first 2 major phases: the preliminary design and the grouting execution. First comes the preliminary design. It consists of 4 steps: geological and hydrogeological investigations, and define the requirements on grout curtain, design of grout curtain, and then design of grouting work. So the first step is the pre-investigation for the dam project, basically, including geological and hydrogeological investigations. So in the geological investigations, the fracture patterns and rock properties shall be investigated. And in terms of hydrogeological properties, and the permeability or the hydraulic conductivity of the rock mass and the fracture aperture can be evaluated by performing the Lujon test, or called water loss measurements. The second step for the preliminary design is to define to define the requirements on the grout curtain. So in principle, the priority focus of the grout curtain is to reduce hydraulic conductivity of the rock mass. So we want the grout curtain to perform and reduce the hydraulic conductivity below a acceptable level, and this level can be chosen from the standard textbook or grouting textbooks, or from in Sweden from RIDAS, as also some regulations limitations on the residual hydraulic conductivity after the grouting in relation to the dam head. And the second requirement is to reduce the uplift pressure, and this can be done also together with working together with the drainage, and also to avoid internal erosion of the fracturing filling material. This can be controlled by the limiting the hydraulic gradient in the grouted area. The third step of preliminary design is to design the grout curtain. It's mainly about the position, the thickness, and the depth of the grout curtain. So here, the difference, it is the difference between this new design concept and the previous empirical ones. Here, the design of the grout curtain is to see it as a structural component of the dam foundation, instead of a foundation treatment under the dam. So then it can be designed as having its own thickness and depth. The position is close to the heel of the concrete dam. For embankment dams, it's under the impervious core. The thickness will be discussed in detail in the next slide. And the depth of grout curtain is related to the Lejeune test results, since once the Lejeune value or the hydraulic conductivity is lower than the required value, we don't have to go deeper than that to build the grout curtain. The thickness of the grout curtain here is the main parameter to achieve the requirements of the grout curtain. So it's corresponding to the three requirements there previously mentioned: permeability reduction, also hydraulic conductivity reduction, and uplift pressure reduction, and the prevention of internal erosion of infilling materials in fractures. All those three factors, they can be analytically related to the thickness of the grout curtain here. So the way to find or to determine the thickness will be introduced in the design example later. Then comes with the design of grouting work. So here it should be mentioned that the design of grouting work and the design of grout curtain, the difference between these two steps. The design of grouting work is to design the process or the plan for the grouting to obtain the predefined grout curtain geometry. So the design of grouting work mainly, after this step, we will determine the grout pressure, the stop criteria, and grout hole layout. Of course, also the contingency plans and complete criterion for the execution application. Among those four, the grouting pressure and contingency plans and complete criterion won't be discussed in detail in this presentation. The stop criteria and grout hole layout is the main focus in this presentation. So firstly, the stop criteria. Previously, it was called refusal, and in this new design concept, we use the time grout spread versus time as this new stop criteria. So for each grouting run, we we know the fracture aperture and the properties of the grout material and the grouting pressure, we can have a curve like these to determine the relationship between the grout spread versus time. So any point on can be the stop criteria. There's no fixed stop criteria, but it should be determined at the same time with the grout hole layout. So it will be. We will come back to this later on. And if we want to have an additional stop criteria, volume can be also calculated, just to assume this 2D spread, 2D radial spread, and with the aperture of the fracture, we can estimate the volume in each grouting run. And for this curve, it is actually, if we normalize, or we have the relative grout spread and the relative grouting time for 2D radial spread, it is the unique expression or unique curve for all the 2D radial spread, and then we can include the typical or special properties for each type of problem by involving the fracture aperture and the other parameters into the calculation. Here, it is to be mentioned that the aperture that we're using, it should not be a very small. We should not focus on aim at sealing very small fractures, such as this B critical. This B critical is the property of the grouting, property of the grout above which the grout can flow freely. So this aperture above which the grout can flow freely. It is not necessary to aim at sealing these very small fractures, since it will take very long time, and it won't obtain much better, much longer grout spread. And to deal with this, we have a boundary fracture aperture, which is defined as the fracture aperture above which a fully sealed fracture can be expected. So this boundary fracture aperture is not normally larger than this big critical. We have mentioned that it is the stop criteria is not a single point on that curve. That should be determined together with the grout hole layout. So the grout hole layout and the purpose for this design of grouting work is to achieve the thickness of the grout curtain. And the thickness here, it is not, if we assume 2D radial spread, grout spread, is not the twice of the grout spread, which is the diameter of the grout spread circle. It should be the thickness, it should be the overlapping between the two adjacent grout spread. And the thickness is less than this twice the grout spread. In general, we can have two directions to go. The first one is to have like shorter distance between among the holes, and we will require less grout spread and less shorter grouting time. And another direction to go is to have a longer distance among holes, and then we will require longer grouting time and a longer grout spread to achieve the same thickness. So that will mean that we will have different shorter grouting time for shorter grout spread, or longer grouting time for longer grout spread. So that is how we determine the grout hole layout together with the stop criteria. Then we go to this grouting execution phase. In this phase, the practitioner or people who execute the grouting should follow the observational method very strictly, and the data on the grout volume grout flow versus time should be collected and analyzed during grouting, and it should be also the hydraulic jacking should also be monitored with extensometers at the rock surface, or by analyzing the grout volume or flow data. Once the volume shows a sudden increase or flow shows sudden increase, then it can indicate possible hydraulic jacking. So if those unexpected behavior of the rock occurs, then we will analyze the reasons and apply administrative actions, including alternative design or other actions, and go back to restart the grouting. When to determine that the grout curtain has been completed, it should be checked about the residual hydraulic conductivity. Go back, like we will go back to the initial requirement there. This will be evaluated also by regional test, but in other additional control holes. Then I'll show a very simple simplified design example. It's about concrete dam, and the focus will be only on thickness and stop criteria and the ground hole layout. So firstly, the thickness. To plot the curve like this, interpret this diagram on the left as uplift pressure, and on the right axis is the hydraulic gradient. So we want to have either the lowest or the smallest point of the uplift pressure, or the hydraulic gradient, which is lower the limit, the critical hydraulic conductivity. So in this case, it is the hydraulic gradient, which is lower than the critical value, happens after the thick with the bigger thickness than 0.5 meters, and the lowest point for uplift pressure occurs in this 4 meters of thickness. So we will pick this 4 meters of thickness since it fulfilled both the requirements there. And the curves expression is shown in here, and it's analytical expression. In terms of stop criteria, since we have decided the thickness as 4 meters, and we would like to determine the stop criteria as well as the grout hole layout. So for shallower section, since it's more prone to the hydraulic checking, so we will choose the less with the lower grouting pressure, and the deeper sections we can go for higher grouting pressure. So we will have to reach a very short grout spread for the shallower section by the jacking requirement, and the deeper sections we can have longer grout spread. So that will result in the grout hole layout looking like this. So we have primary holes which go through all the way through the bottom of the grout curtain. In this case, it will be 20 meters in depth, and we will have the grout spread of 3.3 meters in the deeper sections, with the spacing between the primary holes of 4 meters. We will have a overlapping thickness of 5.2 meters. And for shallower sections, we will have, including also the secondary holes with a 3-row setup. Between the rows will be 1.5 meters, and between the holes in one row, it will be 2 meters, and the grout spread in the shallower section will be 1.3 meters. With these 3 rows, we can have a thickness of 4.6 meters, which fulfill the requirements and give us the indication of grouting time needed for each grouting section. The final grouting plan will give the top view and also as well as the side view. So it will be in all the way to 20 meter with 5 grouting sections, and the grouting should be performed upwards from the deeper sections to upper sections. And it will also indicate the grouting time and grouting pressure and the additional volume stock criteria for each grouting run. Before we go to the final future plan, the SVC report design of grout curtains has been completed, and it contains the more detailed description and discussion on the new design concept. So today's presentation is a short summary for of the report. So it is still in the process of being published on the Energiforsk website, and hopefully will come out soon in the future. And if you want to learn more about to know more about this design concept, you're more than welcome to visit this website and read the report there. About the future work, since as previously as Martin said, the grout curtain will degrade with time. So remedial grouting is probably more of a demand than grouting under new dams. The research on remedial grouting design will be possible future work, and the grout erosion during the remedial grouting under the strong flow beneath the dam will be laboratory, and of course the case study on the real grouting project under the dam you'll be aiming to investigate the grout spread versus time in natural rock mass with the influence of rock roughness and the intersection of the fractures, and to investigate the grouting's effect on uplift pore pressure and hydraulic gradient by measuring the uplift pressure, water pressure changes before and after grouting, and also to evaluate the applicability of the grout design concept, which is very helpful for the design concept as well itself. So thank you very much. I hope I'm on time.
Yes, sir, you are on time. Thank you very much. We do have time for a question or two before the break. I was thinking, and this could maybe be also for Martin, we were talking about remedial grouting. To what extent will it be a complication that this ground has been grouted before? We are not talking about sort of fresh ground, but I suppose it could be equal to jointed ground with fill material. But will it be a difference because it's grout and not normal fill, natural fill material? Have you any thoughts on that?
I think the penetration of the grout, I mean, it's governed by the aperture of the joints, and if it's grouted before but has some leakage ways or cracks in it, I mean, you will still have the same penetration. So it should not matter if it's grouted before or not. Probably you have less grout take, but the penetration will not be influenced.
Yeah, you also, if we perform grouting in the previous grouted material, then if we perform the Lujon test, water loss measurement, it will just represent the property now.
What could be, I mean, somehow it can govern which aperture distribution you have, because you have a number of different fractures in a rock mass, and perhaps if you have a grouted rock mass, which type of distribution you have of the open fractures. that could be influenced, and that might be necessary to take into consideration for some of the calculations that we do in this concept.